Hello students, in this video I am going to answer to the previous year's questions from 2023 to 2025 of AHSEC first year examination, final examination under Assam Higher Secondary Education Council of Physics, Chapter Gravity. Okay, so before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. That's my Insta ID. You can follow me on Insta. Okay. So now let's start. So here is the first question. Establish a relation between escape velocity and orbital velocity. Okay. So now let me answer to this question. So first let me clean these things. Okay. So here you see, now you see the escape velocity or the minimum velocity okay, required for an object to reach infinity okay, is given by V is equal to root over capital G is given by 2 root over capital G capital M by R plus H. Okay, that means if here R is the radius of the earth and mass of the earth is suppose capital M, and the object is at a distance of R plus H. That means H is the height of the object from the surface of the earth. If the object is not on the surface of the earth, and then the minimum speed or velocity required to throw this object so that it doesn't come back to the earth's surface or to reach infinity, that is called the minimum velocity. That minimum velocity required is called the escape velocity. Okay, so here let me mention here, M is the mass of the earth, and R be the radius of earth, and H is the height of height from where the object is thrown. Okay, thrown to infinity, right? So this is suppose equation number 1. Now you see what is the orbital velocity. So orbital velocity, suppose this is a satellite, and it is revolving in this orbit whose radius is R plus H. Okay, in that case the minimum velocity required to maintain this motion at this height is the orbital velocity in this orbit. Okay, so first let me clean this diagram. Okay, so here, so let me divide the base. Okay, and the orbital velocity, let me write here, orbital velocity of a satellite of a satellite to revolve around the earth in a orbit of radius r plus h is given by VO is equal to root over capital G capital M by r plus h. Okay, I hope you know these things. So these two are known to us. Okay, so from equation number 1 and 2, what we can do, so first pause the video and note these things. Okay, first let me write these two expression, let me copy these two expression and let me go to a new slide, as I have not enough space here. Okay, so these are the two equations we have got. You don't need to repeat this. Okay, just write one equation once, as I have changed the slide, so that's why I have written these two equations again. So now you see, from these two equations what we can do here, equation number 1 divided by equation number 2, that's going to give you VE by VO root over 2G M by R plus H divided by root over G M by R plus H, and if you divide these two, then you're gonna get root 2 only, and remaining terms will be cancelled, right? So that's gonna give you root 2. So therefore VE is equal to root 2 V naught. Okay, root 2 V naught. So this is the required relation. Okay, this is the required relation. Now you see, this same question was asked in 2024 also, but it was asked in different manner, so that the ratio of escape velocity and orbital velocity is root 2. So here you see same question, from here you can obtain the ratio. So simply just V by V naught is equal to 1 by root 2. That's what you are asked to show. So this ratio is ratio is root 2. That is what we need to show. Okay, same question. So hope you have understood this. So now let's move on to next question. Before that, let me tell you, this question was asked in 2024 and also it was asked in 2025, same question. Okay, so don't need to be confused here. Okay, so now let me take the next question. Here is the next question. State and explain Kepler's 3 laws of planetary motion. So let me explain one by one. So now let me explain. There are 3 laws. Okay, let me explain one by one. So here is the first law. All the planets, okay, move in elliptical orbits, okay, with the sun situated at one of the foci. Okay, one of the foci. Okay, you can add one more thing. All the planets move around the sun in elliptical orbits with the sun situated at one of the foci. Let me rearrange these lines. Okay, so that's how you can write. Just give me a second. Okay. Now you see, the orbit of the planets which are revolving around the sun are not circular, they are elliptical in shape. What do you mean by ellipse? First let me tell you. So this kind of shape is called ellipse. Okay, so here is the major axis and here is the semi-major axis, minor axis. This is called major axis, and here is called minor axis. Okay, and it has 2 foci. Okay, this is suppose F1 and this is suppose F2. So here is the planet. Suppose let me take this is the planet, and here is the sun. Sun should be situated at one of its foci, and let it be the sun. This is the sun. Let me write it S. Okay, let me write it completely sun, and this is the planet. Okay, now you see. So what is ellipse? Now let me take suppose if this is an ellipse, if this is ellipse, then here you see, and if this is one of its foci, okay, then if you take any point on this ellipse, okay, then what you're gonna have. So distance, let me write the both foci. This is f1, this is suppose f2. Okay, suppose if you have taken this distance and taken this distance, so this is suppose p1, this point is p1, then p1 plus p1 f1 plus p2 f2. Okay, sorry, not p2, p1 f2, p1 f2. Okay, so distances from this point to this foci is sum of the distances of any point on this ellipse. Okay, from any point, sum of the distances from any point on the boundary of this ellipse to the foci must be always constant. That means suppose we have another point here p2, and now let me take take these two distances f2 p2, f1 p2 and f2 p2. So p1 f1 plus p1 f2 must be equal to p2 f1 plus p2 f2. Okay, then if you take similarly one more point here, then distances, sum of the distances from this point to this foci also equal to these two sum of the distance, right? Hope you have understood this. Then it will be called an ellipse. So now let me clean this. Okay, so now you see, so here this is the sun, and let me represent it by S, and here is the planet. Okay, so this is all about the first law. Okay, so in this figure, P is a planet and S is the sun at one of the foci of the elliptical orbit. Let me make it F. Okay, elliptical orbit, right? So now let me write the second law. Okay, let me write the second law. So now let me copy this diagram so that I can explain the second law as well. So here you see Kepler's second law. So what does it say? So according to this law, the line joining these two points S and P, that means line joining the sun and the planet, okay, it sweeps equal area in equal interval of time. Okay, let me write that. So here you see, this is the orbit, and here is the planet P, and this is the sun. Okay, this is the line joining the planet and the sun. Okay, it is moving in this way. So this is the planet. Okay, so to cover this distance, suppose it took 10 days. Okay, then the area swept by this line joining P and S is suppose this. Okay, and the same area will be swept by this line in the next 10 days. Okay, that area will not be different. Okay, so that's why to maintain this aerial velocity, to maintain this aerial velocity when the sun, when the planet which is away from the when it is away from the sun, then it moves slower, because when it goes very small distance, the here you see, if you consider these two position, okay, now you see this area and this area, okay, when it will be equal, if these two areas are equal, then it is obvious that this distance is smaller than this part, okay. And if these two areas are equal, then both must be covered in the same number of days, or in the same interval of time. In that case, as it covers less distance here, so it must be slower, and it must be faster at distance when it is closer to sun, okay. From that concept, this law was explained. So now let me clean these things, okay. So let me write here. This law comes from the observation that planets appear to move slower when they are further from the sun than when they are nearer, okay. Right, now you see, let me draw something here. So this is the line joining P and S. So now here you see, this is the P after suppose time interval del t, okay. Then this area, now you see, when the planet is at this position P and it moves from this position to this position, then here you see area swept by this line will be equal if it takes the same time interval del t, right. Then these two area will be equal. So let me name it. This point is S, this is suppose P1, this is P2, so this is P3, P4, okay. So if del t is the time interval, to time interval for the planet to reach P2 from P1 and P4 from P3, then area SP1 to this area SP1 to, this is P2, this is P1, right. Let me write that way, okay. It must be equal to area SP3 P4, right. Hope you have understood this. So now let me write the third law, and let me tell you one more thing before I write the third law. Kepler's first law is known as law of orbit, okay, and second law is known as law of areas, okay. Instead of writing first and second and third law, you can it will be better if you write this, and instead of third law you can write law of period, okay, right. So now let me explain the third law, or law of period, third law or law of period. Okay, so according to this law, so here is the third law. The square of the time period, okay, of revolution of a planet is proportional to the cube of the semi-major axis, cube of the semi-major axis of the ellipse traced out by the planet. That means the orbit of the planet. Okay, so now you see, suppose here you see we know that this is major axis, right? This is major axis, and length of the semi-major axis, that means half of the major axis, let it be suppose a, and t be the time period of revolution. If t is the period of revolution of a planet, okay, and a be the length of semi-major axis of the ellipse traced by it, then the third law says that square of this time period is directly proportional to cube of a. Okay, that is the third law. So hope you have understood this. Now let me take the next question. Here is the next question. Find out an expression for acceleration due to gravity of the earth at a height h from the earth's surface as stated below. So we need to obtain this expression. Okay, suppose this is our earth. Okay, this is the earth, suppose, and here you see radius of the earth is capital RE as given in this expression, and here is a point A, suppose, which is at a height h from the surface of the earth. Okay, from the surface of the earth, this height is h. Okay, and this is another point B on the earth surface. Okay, now here you see we know the relation between small g and capital G, that is given by small g is equal to capital G capital M by r square. Okay, where r is the radius of the earth, so here we're gonna write RE, and M is the mass of the earth. Okay, we know this relation. Okay, so acceleration due to gravity let me write it properly. Acceleration due to gravity at the point B on earth surface is given by small g is equal to capital G capital M by RE square. Okay, so this is equation number 1. So here you know mass of the earth, M is mass of the earth, and RE is the radius of the earth. It is the radius of the earth Okay, so now let me write it properly. Okay, now if you find the acceleration due to gravity at this point A, here you see the figure. So at B, acceleration due to gravity is g, small g. Okay, here at this point it is small g, and at this point it is suppose g dash, or let me write simply gh. Okay, so acceleration due to gravity at a point A at a height h from the surface of the earth. So acceleration due to gravity at A, okay, which is at a height h from the surface of the earth or earth's surface, that will be given by, let me write that one here, okay, ZH, that will be given by capital G, capital M. Now distance from the center to this point A is, this distance is R plus H, because capital R is the, sorry, here it will be RE plus H, RE plus H. So RE is the radius of the earth. Okay, so hope you have understood this. Now you see here, instead of RE we're gonna write here now RE plus H whole square, right? Okay, we're gonna write that. So hope you have understood this. Okay, now you see, okay, this is suppose equation number 2. Now divide 2 by 1. Okay, now here you see it is clear that from this expression, now compared to this denominator is greater, that means this number is smaller, so that's why value of H decreases with increase in height, right? So we can write that. So now this is suppose equation number 2. Now equation number 2 divided by equation number 1, if you do so, then you're gonna get GH by G, okay, is equal to, let me write this one here. Okay, so here is the value of GH, and let me write the value of G, small g. So here is the value of small g. Okay, so here we can cancel capital G, capital M, and if you simplify this, then you're gonna have what you're gonna have, GH by small g is equal to RE square divided by RE plus H whole square. That's what we're gonna have. Okay, let me copy this expression and let me take a new slide. Okay, so let me take a new slide. So what was the last equation we have got? This one. Now if you see RE square, now let's take common R square from this expression. Then if you take RE square common, then within bracket we're gonna have 1 plus H by RE whole square. That's what you're gonna have, right? So now you see RE plus H, if you take R common from this expression, then you're gonna have R plus H by RE, right? So if we have whole square here, then here we're gonna have squares, right? So hope you have understood this. Now if you cancel these two, then you can write this 1 by 1 plus H by RE whole square, right? And which is nothing but 1 plus H by RE whole to the power minus 2. So now you see, if you use binomial expansion, that 1 plus x whole to the power n is equal to, here if you put minus n, then what you will have, 1 minus nx by factorial n, then plus, okay, and then n into n plus 1 by factorial 2 x square, then minus again, wherever you get odd power on x, then that term will be negative, n into n plus 1, n minus 1, sorry, not minus 1, n plus 2 divided by factorial 3 x cube dot 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 so on. Okay, if you apply that, then this expansion will be like this, 1 minus 2h by RE, then plus we're gonna have more terms, than 2 into 3 by factorial 2 h square by RE square and so on. But here the terms, where the terms containing higher powers of this factor h by RE, those will be neglected. Okay, when these two when these terms on what condition these terms will be neglected, that condition is if h by re is very less than 1, okay, that means when h is very less than re, in that case h by re will be very less than 1, then we can write gh by z is equal to, sorry, let me write this properly, that's what we're gonna have. So here, using binomial expansion, and neglecting the higher powers of h by r, okay, we get gh is equal to 1 minus 2h by re into z. Okay, that's what we can write. Or here you see, we are to show this expression. So this is what we have got, but in the question z is written here, that's it. That is the only different thing, same expression, right? So we have got it. Okay, so now let me take the next question. Okay, here you see, fill in the blanks. So we need to fill up the blanks by these words, okay, polar satellites or geostationary satellites. So here you see, so first one will be geostationary satellite, okay. So geostationary satellite, I am writing here GS only, but in exam don't write like this, okay, write it completely. And next one should be polar, I am writing P here, okay, as not enough space. And the next one is again geostationary, and next one, the fourth one will be the geostationary, okay. So only 2 is polar, okay, and 1, 3 and 5 geostationary, okay. So next question. So here you see, the kinetic and potential energy of orbiting satellite of mass 1 gram are given by these two expressions. We need to find the total energy, okay, total energy of an orbiting satellite of mass m. So now let me write this too. So kinetic energy and potential energy of a orbiting satellite are given by these two expressions. Kinetic energy is capital G, capital M, E means mass of the earth, by 2 Re plus H, and potential energy is G Me by again Re plus H. So here gravitational potential energy is negative, so here we can write negative here. So therefore total energy is given by kinetic energy plus potential energy, okay. This is for the 1 gram mass satellite of mass 1 gram, okay. So that let me write this one here. So what will be the total energy for 1 gram satellite? Let me write this. First let me put the value of kinetic energy, that is this, and then plus potential energy, which is negative of this is the potential energy, so minus plus it becomes minus, right? So hope you have understood this. So now from here what you can do, you can take Z capital M E by R plus Re plus H, it can be taken common. Then here we're gonna have half minus 1, and half minus 1 is nothing but minus half, so we're gonna get minus 1 by 2 of G Me by Re plus H. That's what we're gonna have. Now we need to find the total energy of an orbiting satellite of mass m, Okay, so total energy of the satellite of mass m should be multiplied m by m should be multiplied by this expression, then you will get total energy. Okay, so here you see, let me write here, total energy of a satellite, orbiting satellite. Let me write here, orbiting satellite okay of mass m is, that will be given by, is, let me write this one in black. Okay, in black ink. So that's going to be capital G capital M E multiplied by small m, okay, by 2 R E plus H. So this is the total energy. So hope you have understood this. Now let me take the next question. So here is the next question, which was asked in 2023. Explain how acceleration due to gravity of Earth changes with altitude and depth. So how does it change with altitude, that we have already discussed here in this question. Okay. So from this expression we can say this was already asked here in 2024, right? So here I'm not gonna explain this again. Instead of that, we're gonna discuss about how does it vary with depth. Okay, so how does it vary with altitude or height? We can write here, it is observed. After writing up to this step, we can say that it is observed that value or acceleration due to gravity, let me write it properly, acceleration due to gravity decreases with altitude, increasing altitude. Okay, right? Because you see, if the value of h increases, altitude increases, then value of this fraction increases, and if you subtract greater value from 1, then you will get lesser value. That's simple, right? So now let us discuss the variation of z with depth. Now let us discuss variation of z with depth. Okay, now you see, here is the Earth, suppose, and here we have a point at depth d. Its depth is d, and radius of this Earth is, suppose, capital R. Okay, mass of the Earth is, suppose, capital M, right? So we know that acceleration due to gravity on Earth's surface, okay, is given by z is equal to capital G m by r square, where capital M is mass of the Earth, and r is equal to radius of the Earth. Okay, now you see, let me consider that rho be the density of the Earth, then m will be equal to, mass of the Earth will be equal to, we know that mass is density into volume, so rho and volume, considering this is to be sphere, volume of sphere 4/3 pi r cube. Okay, and if you use this value here, then you will get z is equal to capital G let me write it properly. Capital Z, instead of m, if we write rho 4 by 3 pi r cube divided by r square. If you cancel this r cube by r square, then you will get only r. So capital Z becomes value of small z will be this now, 4 by 3 capital Z rho pi r. That's what we will get after putting this value here, right? Hope you have understood this. So now you see this is z. So let me take this is equation number 1. Now what will be the value of z at a depth d? Let me take that gh. Okay, gh, acceleration due to gravity at depth is suppose gh. Okay, now when you consider the point at depth d, then distance from the center to this point is r minus d, right? And in that case, now you have to use the mass of this portion only. Okay, the sphere of radius is r minus d. Okay, we're gonna take the mass of that portion only. So we're gonna ignore this outer part. Okay, so hope you have understood this. So now here you see, let me write this one here, just give me a second. Okay. So now acceleration due to gravity, let me write this, acceleration due to gravity at a point below the Earth's surface at depth d is gd. Let me write it gd. Okay, gd is equal to capital Z. Now mass will be obtained by multiplication of density into volume, 4 by 3 pi. Now we need to take the volume of this part only, that is r minus d whole cube, and divided by, and you know distance to that point which is at a depth d from this center is r minus d. So r minus d square, r minus d square. Okay, so now let me copy this expression and let me go to next slide. So here is the expression. Okay, and let me copy the first equation as well. You don't need to repeat these equations, just I have changed the slide, that's why I have written here again. So now if you cancel this by this, then you're gonna get this 4 by 3 capital Z rho pi then into r minus d. This is 2. Divide equation number 2 by equation number 1. So we're gonna have just give me a second, gd divided by z is equal to, now let's put the value of z d. This is gd. Now value of z is this. Let me copy this. Here is the value of z. Okay, now here this part is cancelled, right? These two parts are cancelled, so we're gonna have r minus d by r, which is nothing but 1 minus d by r. So here also you see, if d increases, then this fraction increases, and if you subtract greater value from 1, then you're gonna get lesser value, right? So here you see, so this implies that gd is equal to 1 minus d by r into z. So value of z decreases with depth. That's what we can say, right? right? So hope you have understood this. Thank you for watching. See you in the next video. Bye bye.